Hello and welcome to Kudo Weekly. I'm your host Johan Pontus, and today I want to talk about reductions. So let's say we have many values and we want to reduce this to a single value. Maybe the max or the sum of all these values, or we want to do some binary operations, say in XOR. Now, there is a cool instruction for that on newer GPUs where we can do this in a single operation. But if you're not working with the bleeding edge and well, you're stuck with some older hardware, there is actually a post by NVIDIA telling you how to do this. Unfortunately, that's not the most efficient way to do it, so I'll show you a better way. Let's get started. Let's say we want to reduce 1,000 items into one. Maybe you want to add all the items together. You want to take the minimum or the maximum. For this example, we'll take the maximum. So there are a couple of ways to do this. Now, a while ago, NVIDIA told us that, well, using shuffle instructions, like you see here, is the best way to do this. Is this still the case? I think things have changed now that we've got newer GPUs with a different mix of instructions and features and optimizations. Let's have a look how the shuffle holds up. Let's have a look at the code. Now we start out with a arbitrary number x. In this case, I've set it to the thread ID, so it runs from 0 to 1023. That means that if the optimizer was really smart, it could figure out that the maximum is the highest thread value, but it's not, so we could. Then we divide the work into 32 warps. So for that, we track the warp ID, and we have 32 shared uh, boxes, the form of this array, to store our values in, one per warp. We run this loop 5 times, so we get 5 timings. That will hopefully allow us to weed out spikes. Next, we start the clock, as in start, in order to make sure that the optimizer doesn't reorder these things on us. We mark these things as volatile. And then we loop 5 times to run a shuffle down. What that does, it takes all the threads, it makes them show their value of x, and then a particular value gets to be selected. The first one is one shifted by 0, so that's still 1. So that means the thread next to the current thread gets to be selected, its neighbor. We put it into y, and then we select the maximum. So the x is now reduced by a factor 2. Every x is the maximum of itself or the neighbor. We then increase the step size by 2. So now we look at x from the neighbor 2 down, take the maximum of that and repeat that until we've looked at all the values. We need only 5 loops because, well, the log2 of 32 is 5. So at the end, we've got every warp has its 32 values reduced into 1. We store these values into a shared array, Then we need to synchronize all the threads to make sure that everybody's up to date. Once that is done and all the threads have arrived at this point, we only need one more reduction, namely the 32 values in SMax. I do the same reduction all over again, but this time just one warp and store the value. We print out the results. We of course do this in a single thread because we've reduced X to a single value. Let's run it and see how fast it goes. So you can see the timings actually differ quite a bit. Let's maybe run it a few more times to see if these timings stabilize. When we run this, you can see that these times, well, the first time doesn't look very realistic and the last time looks suspiciously fast. So we'll take these times in the middle. So it runs somewhere around 1700 cycles. I think the optimizer here has found a way to cut the end of the loop. So I don't think this time is realistic. So about 1700 cycles, which is slightly more than 2 cycles per value. Let's see if we can do this faster. We were using a shared array here, and we have really efficient atomic operations on shared data. So let's have a look how fast that goes. I'll copy this whole thing and make a few changes. When we run the atomic version, we can see that this runs quite a bit faster. 280, 280 looks about right. So the first part is the same, except we generate a lane ID, which is the thread ID within a single warp. And then all threads zero out as max, because we're going to manipulate these later and we don't want the maximum values to be affected by whatever happens to be in shared memory before. We need to synchronize the threads after that, because otherwise some threads might be already running atomic max and other threads are going to be zeroing this out. Then we run on all threads at atomic max. We could run this on a single value, but that's going to make 1,000 threads hammer a single value, which is not optimal. Instead, we make this thing to take the maximum within each lane. Now these warps execute pretty much as a unit. So it means that here's the minimum of contention that we can generate. And these warps will, well, some of them will execute at the same time, but lots of them will execute one after the other. Then we synchronize again so that everybody is up to date. Now, obviously, warp 31 will have the maximum values here. Then we take a single warp and we read in X and do the same atomic operation, but now on a single value. Now at this point, we don't need to synchronize the threads, but we do need to synchronize the warp. Around about 290, 300. Let's call it 300 instead of 17 and a bit. So that's a fair increase. Let's see if we can do better than that. There is on the Ampere GPUs, there is a instruction called reduce sync, which does what it says on the tin. It reduces data in a single instruction. When we look at the code here and we compare it against the atomic code, we can see that we no longer need to zero out the shared array because we're assigning the maximum value from each warp to it directly. Then, of course, we need to synchronize so that all warps are aligned. For an arbitrary warp, in this case 0 out of those, we load the value into X and then we reduce X down to a single value. Now we do not need to synchronize after it because reduce max is a synchronizing instruction. So it synchronizes all the partaking threads into a single value. Then take the end clock. Let's have a look at how that runs. We can see that it runs slightly faster than the atomic one in about 190 cycles, all about a third faster than the atomic, which runs in about 300, and significantly faster than the shovel. I would like to leave it there. So if you have some reductions to do and you have a new enough CPU, obviously the dedicated reduction instructions are the way to go. And if not, Atomic is your friend. I hope you found it informative. Thank you for watching, and I'll see you next week.